In this video, we'll be discussing p-values. So what exactly is a p-value? Well, using the Prove It study, which compared pravastatin versus atorvastatin after an acute MI, in that particular study, they had their primary outcome of death or major cardiovascular events. And you can see the event rate was 26.3 with pravastatin, and atorvastatin was lower at 22.4% or better. And really the question would be is, that difference that we're observing, is that due to random chance alone, or is atorvastatin truly better? And using inferential statistics with p-values, it helps us answer that question. So a p-value is the probability of seeing an effect as big or bigger due to random chance, assuming that the null hypothesis is true. So going back to the Prove It study, the p-value in this case was 0.005. And the difference that we observed, the absolute risk reduction, was 3.9 percentage points. So what does that actually mean? So the p-value of 0.005 is the same thing as 0.5%. It means that there's a 0.5% chance that if atorvastatin is not actually effective, so if the null hypothesis is true, that in this trial that we would have observed a difference of 3.9 percentage points or even a larger difference than that. Or in other words, it's really, really unlikely that if atorvastatin is not effective, that just by chance that we would see this numerical difference of 3.9 percentage points. So if you imagine repeating the Prove It trial 100 times, and on a number line we kind of graph where we're at. This particular time that we ran the Prove It trial, we saw a difference of 3.9 percentage points. So what that means is another way to think about a p-value is asking the question, how often would you need to repeat the Prove It trial to show a difference of 3.9 percentage points or more, assuming that it doesn't actually work, assuming that atorvastatin is not better than pravastatin? And our p-value tells us that. It means that 0.5% of the time, if you were to repeat the Prove It trial, you would observe a difference of 3.9 percentage points or greater, assuming that atorvastatin is not better than pravastatin, or assuming that the null hypothesis is true. So when it comes to p-values, there's a type of error called a type 1 error that we need to be aware of. And the type 1 error is a false positive result. What it means is that we conclude that there's a difference. We conclude that atorvastatin is better than pravastatin when it actually isn't. So concluding a difference is there when one does not actually exist. And the p-value is actually telling us what the probability of that type 1 error is, assuming that the null hypothesis is true. So in the Prove It trial, our type 1 error rate is 0.5%, that this was due to random chance alone, or in other words, a 99.5% chance that this was not due to random chance alone. So in clinical trials, we have an alpha threshold of 0.05 or 5%, and that refers to our threshold at which we consider something to be statistically significant or not. And this is somewhat arbitrary of 0.05%. But it is widely agreed upon. There are some exceptions that exist to this, but the reason that we pick 0.05 as our alpha or our type 1 error threshold is that if we wanted a smaller value of 0.01 or 0.001 as a threshold, it would require more patients, more cost, more money. It would take longer to run clinical trials. So we, as a medical community, have more or less decided that this is a reasonable trade-off of resources versus avoiding the risk of a type 1 error. What that means, though, is that 1 out of 20 publications, or 5% of the time, we will encounter a type 1 error, where we conclude that atorvastatin is better than pravastatin, or we conclude treatment A is better than treatment B, when in reality it is not, and that would be called a type 1 error. Now, for better or worse, the p-value threshold of 0.05 is considered absolute. What that means is that if you're less than 0.05, we consider that to be statistically significant. And if you're more than 0.05, you're not statistically significant, which means that we would accept the null hypothesis in that case. So oftentimes authors, when they really believe in a treatment effect and they're really close to that 0.05 threshold, but not quite there, you'll see terms like a trend towards statistical significance with a p-value just above 0.05, or a non-significant increase in whatever the endpoint is with a small p-value which is not less than 0.05. Or there was a trend towards statistical significance with a p-value above 0.05. All of these are common terms that really indicate author bias because again, as a medical community, we've decided that a p-value of 0.05 is our absolute threshold. You are either below it or you're not, and there is no trends or nearly significant value. Now, the other thing a p-value does not tell you is the effect size or the magnitude of an effect. So if we didn't have our percentages between atorvastatin and pravastatin in the PROVE-IT study, and I just showed you the p-value, you wouldn't have a good sense of how effective was atorvastatin versus pravastatin, or even which one was more effective between the two. The p-value literally only tells you that the difference you're observing is due to chance alone or not due to chance alone. So really, we could not answer the question of which treatment arm is better or by how much, because we need both things. We need the p-value in addition to the numerical values between our two arms. Now, the other thing a p-value does not tell you necessarily is whether the difference you observe is clinically significant. So imagine a study that looked at vitamin C for weight loss versus placebo, and the difference in weight loss was 2.44 kilograms in vitamin C and 2.39 kilograms for placebo with a significant p-value. So p-value of 0.04 is less than 0.05, so we would say that this is a statistically significant finding. But if you think about it, the difference here is 0.05 kilograms or 0.1 pounds. Most people, if not all people, would agree that this is not a clinically meaningful effect, even though the p-value is statistically significant. And this is an example of a statistically significant finding that is not clinically significant. Now, another pitfall to p-values is what's called p-hacking. And this is where a researcher will analyze their data, manipulate the data until they find a p-value that is less than 0.05, where they kind of hack the data or hack their analysis. This can be done through subgroup analysis, where they look at a particular group of the entire population that was studied. Could be a variation of composite endpoints, where they look at 2 or 3 different endpoints in different ways and combine them together. Could be that they have secondary or tertiary endpoints when maybe those are not very important, but they still analyze those for p-values. Then post hoc analysis, this means an analysis is done after the fact where it wasn't originally planned to do a given analysis. And the danger with these is that an investigator can run hundreds, if not thousands, of post hoc analyses and only report the 1 or 2 findings that are statistically significant. At the end of the day, the more analyses you do on the same thing, the higher the risk is going to be of a type 1 error, because every p-value has an inherent risk of a type 1 error, and the more p-values you do, the higher that risk ends up being of a type 1 error. Now, just to drive home the point, and this was published in Lancet in the 1980s, a researcher kind of jokingly did a study looking at aspirin versus placebo, and they analyzed the data according to the patient's astrological sign. And this clearly makes no sense that someone's astrological sign would be relevant to whether aspirin works or does not work, but they were doing this to show that p-hacking is something that can be done and can end up showing a significant result. So in this case, they did a subgroup analysis of those that were Gemini or Libra for their astrologic sign, and there was no difference observed of vascular death with aspirin versus placebo with a high p-value. But then all of the other astrologic signs, when you only analyze those and you excluded Gemini and Libra, there was basically a 3.1 percentage point difference with a very significant p-value. Again, this is done in a joking way, but it highlights the point that when you do a subgroup analysis, especially one that doesn't have any biologic plausibility, the more times you analyze the data, the more likely you are to find a significant p-value. So let's do a quick self-assessment. So the NIN study was a study that looked at tissue plasminogen activator, or TPA, versus placebo for acute ischemic stroke. And one of the endpoints was 3-month mortality. For that particular endpoint, it was 17% versus 21% with a p-value of 0.3. So our first question is, assuming TPA does not truly reduce mortality, what is the probability the 4 percentage point difference that we're observing is due to random chance? Pause the video and then answer for yourself. So that probability is 30%. So what that means is that assuming TPA doesn't work, so assuming the null hypothesis is accurate, we observed a 3 percentage point difference between TPA and placebo. The probability of observing a 3 percentage point difference when there is actually no effect there is 30%. So there's a 30% chance that the difference we're observing is due to chance alone, so not a true effect. Question 2 is, in general, what probability of a type 1 error is acceptable? So for this, 5% or 0.05, what that means is that our alpha threshold is 5% or 0.05. That's our risk of type 1 error. If our p-value is below the alpha threshold of 0.05, we reject the null hypothesis and assume that there is some difference observed. And if the p-value is more than 0.05, our alpha threshold, then we accept the null hypothesis and assume that there is no difference between the two groups. So then finally 3, should the null hypothesis be rejected in the NINS trial? And the answer here is no, we should not reject the null hypothesis. We should accept the null hypothesis because the p-value of 0.3 is larger than our alpha threshold of 0.05. Thanks for watching. This video is actually one of 35 videos from ClinCalc Academy's Biostatistics RX online course. If you're interested in developing a rock-solid foundational understanding of biostatistics and medical literature evaluation, check out a link in the show notes, which includes access to the 35 videos, which is about 5 to 6 hours of content, more than 100 comprehensive quiz or exam questions, and even access to a free 10-question exam on biostatistics. Again, link is in the show notes, and thanks for watching.